Next, we consider the spherical coordinates. The domain in rho phi theta space is denoted by omega. Here rho is positive, phi is 0 to pi, and theta is 0 to 2 pi, open intervals. Okay, so the corresponding domain in the xyz space is the R3 xyz space R3. Removing this is also a half space. X is no negative, y is 0, and z is free. Okay, so for this we have this picture. What's the meaning of rho phi theta here? Rho phi theta. Here rho is the point u. Of course, for this point u, we have x, y, z coordinate in the x, y, z space. Okay, but the distance from the origin to this point, u, is our rho. And what's theta? Theta is the you project u into the xy space, and the theta coordinate of the polar coordinate of this projecting point is our theta. That is, in other words, the angle between the x-axis and the segment from 0 to this projecting point, that is our theta. And for phi is the angle between the segment from the origin to our point u under the z-axis. This is our phi. So this is the meaning of rho phi theta. These three quantities determine the point u uniqueness. Okay, so but for the points in the z-axis, we cannot determine the theta. We cannot determine the theta. Also, this phi, therefore, we need to restrict the phi to be phi could not be 0 and could not be pi. Okay. So, moreover, when theta is 0, since when theta is 0 and theta is pi, that is, you go around and come back here, they represent the same point. So we also need to removing theta equal to 0 and pi. Therefore, this is equivalent to remove this half space from the three-dimensional xyz space. So this D is the corresponding domain of omega under the spherical coordinates. The coordinates is given by this map, defined over the closure of omega to R3, which is given by it maps rho phi theta to x, y, z. And x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So, as you can check, this map is not C1 diffeomorphism. I am mistake here. This map is C1, but it is a diffeomorphism between omega and D. Okay. And the Jacobian determinant is given by the determinant of the Jacobian matrix. So this Jacobian matrix can be write out in this way. First, this element should be the partial derivative of x, which is respect to rho, but x is rho sine phi cosine theta. Therefore, the partial derivative of x, which is respect to rho, is sine phi cosine theta. And in a similar manner, you can determine all the elements of this Jacobian matrix. And by a simple computation, you expanded this determinant, which leads back to the last column or the last row, because there is a 0 here. So by some computation, you will find out that the value of this determinant is rho square sine phi. Okay. So you should remember this result because we will use this frequently. Now we go to an example. We compute this integral, triple integral. The integrand is z e minus x squared plus y squared plus z squared, and the integral domain is D, where D is bounded by this surface z equal to x squared plus y squared, and this surface x squared plus y squared plus z squared equal to 1. So the first surface is a cone, z squared equal to x squared plus y squared, and z positive. And the second surface is a sphere, center at the origin, the unit sphere. Here is the picture of the domain. So this is the cone, and the lower boundary of this domain is the cone, and the upper boundary of the domain is the sphere. Okay, so from this geometric consideration, if this domain can be written in spherical coordinates in this way: rho is from 0 to 1, theta from 0 to 2 pi, and phi from 0 to pi over 4. How to determine this? Okay. So since the upper boundary is the unit sphere, therefore every point in the domain, the distance from every point in the domain to the origin will not greater than 1. Okay, will not greater than 1. Therefore the range of rho is 0 to 1. And for theta, because this you can rotate this domain around the z-axis, the domain will not change. Therefore, every point on the rotation remains in the domain. So the theta is the angle of the point to the z-axis, which with respect to the x-axis. Okay, by the geometric meaning of this is the theta. Okay, so the theta for our domain can be run from 0 to 2 pi, but will not equal to 0 and 2 pi. So this is the range of theta, 0 to 2 pi. How about phi? Phi is the angle between the z-axis to the points in the domain. Okay, so in our domain, the maximum phi of course phi equal to 0 corresponding to the z-axis, the upper z-axis, but the maximum phi is the boundary, is when the point goes when the point reach the cone. This is the maximum phi allowed, but because this is z equal to x squared plus y squared, so you consider r squared plus y squared square root of x squared plus y squared to be an r, then z equal to r. Therefore, the angle between this, because z equal to r, the angle between the cone and the z-axis is pi over 4. So this is the range, the maximum possible phi in our domain. So this determined phi is this, given in this way. Okay. Now, having obtained the spherical expression of the domain in spherical coordinate, we can apply the change of variable formula to compute our triple integral over D. So the integral is transformed into a new integral over the new domain. The new domain is the corresponding omega, and the integrand z e minus x squared plus y squared plus z squared is rho cosine phi in our spherical coordinates, and this exponential minus x squared plus y squared plus z squared is e to the minus rho squared. Then the Jacobian determinant is rho squared sine phi. So the new integral is this. Our integral equals this new integral, which new domain and the new integral. Okay. Now, since this phi, this omega, the integral domain omega is is a three-dimensional rectangle. So we can write this using applying the Fubini theorem twice to write this triple integral over the three-dimensional rectangle into iterative integral. First integrated with respect to phi, and then rho, and then theta. Now the most inner integral which is respect to phi, so those terms not involving phi, that is rho cube e minus rho square, can be moved outside the integral, outside the inner integral. Then we compute this integral. This integral we can compute using what we learned in single variable calculus. And also this integral can be computed. Finally, this is precisely 2 pi. So the result is 2 pi this is 1 over 4. Computing this integral, you will get 1 over 4. Therefore, the middle integral is 1 over 4 rho cube exponential of minus rho square. And this integral can also be computed. You take a rho from rho cube and move. Therefore, rho d rho is d rho square. Half of d rho square. Then d rho square in the integral, you can replace the rho square by t. So this integral becomes 1 over 8, because I need to take 2 to make d rho square. 1 over 8 t square exponential t exponential minus t dt. So this can be computed. So the result is this number. So this is the final result for the computation of this integral. Okay.